Okay, so this week we will be doing waves on the stream. And so the concept of this is that when you have a wave generated by a mechanical driver, it's going to set up a standing wave within two rods that has a length tied to those rods, and then at certain frequencies, then you will find that there are standing waves, traveling, in the traveling on the string, and you want to find exponential value of the velocity, how fast do those waves travel. Okay, so in other words, the objective of this experiment is to investigate standing waves on the string, and what is the relation between tension in the string, the frequency of the oscillations, the length of the string, and the number of segments in the standing waves. So you might wonder what exactly are the standing waves. So to give you some ideas, so basically this is what you have here. So we will have like two rods, and then there's a string tied to both rods. So the length of the string in oscillation, we call that capital L. That capital L is not the total length of the string, but it's just the length of the string in oscillation. Okay, so when we talk about standing wave, it just means that you have the wave that can be supported by this arrangement, and you'll find that not all frequencies will support standing waves. Only at specific frequencies that standing waves can exist. So when we say standing wave, it just means that once it's been set up, it's going to show out a pattern like this. And in addition to that, the amplitude of the standing wave will be a maximum. So in other words, when you do the experiment, there might be frequencies that give rise to oscillation, but then you want to find the right frequency that produce the maximum oscillation. Okay, so that's basically this is what we call the standing waves. And so standing waves basically produced by when you have the wave parts traveling on the string, and then there's an incoming. So let's say coming back to this diagram. So let's say you had a wave that's produced on one end, and it's going to travel on this string, and then when they encounter the end, it's going to reflect it back. So you have the outgoing and the income. You have the outgoing and the reflected wave interact with each other. So we use the superposition, meaning that you have the two waves adding together, and then they're going to produce at specific frequencies. Then standing waves can be produced. Okay, and when the standing waves are produced, we say that it is the resonance frequency. Okay. All right, so the waves can be described sinusoidally like this, and let me see. So all this, you can read about that, but let me just say that there are several terminology you need to know. So when we talk about when we use the capital A here, this indicate antinodes. Antinode meaning that that is the location when you have the maximum amplitude. So for example, at this point, you have the antinode, and at this location, that location, you had two antinodes, and for this arrangement, you have three, and then for this one, you have four. You'll notice that when you have one antinode, we call that n equal to 1. When there are two antinodes, we call that n equal to 2, and so forth. So the n here, the lowercase n here indicate the mole number, okay, or we call it harmonics. So this is what we call the fundamental or the first harmonics, and this is the second harmonics. This is the third harmonics and fourth harmonics. So the n here refers to how many n's that it has, and also what is the mole number. Now, what about the N here? The capital N here indicate nodes. Nodes are the locations where there's no oscillations. So zero oscillation or zero displacement in the vertical direction. So you have, for this one, you had like you had two nodes, one antinode. For n equal to 2, you have three nodes, two antinodes. And for n equal to 3, you have 1, 2, 3, 4. You have four nodes, and 3 antinodes. Okay, and in addition to that, you'll notice that take this, for example, this is like one complete circle, one period. So from this point, from this end here, going through another end and coming back to another end here, that indicate this is what we call the one wavelength. So you can see that when n equal to 2 in this arrangement, that the wavelength is equal to the capital L here. Okay, and so after you go through this, you'll find that the wavelength and the length of the string in oscillation, they have a very simple equation to describe the relationship between those two. And that equation is this: lambda sub n, lambda is a wavelength, n is a mode number, is equal to 2L over n, and n is 1, 2, 3, and so forth, which which is an integer. So you can see that lambda 1, when first harmonics, the wavelength is two times the length of string in oscillation, and when n equal to 2, the wavelength is just equal to L, just as shown here. Okay, so this describe equation 3 describe how the length of the string in oscillation in relation to the wavelength of the wave that is supported. Okay, and the other thing is that if you look at this, if you look at the separation between two antinodes, you'll find that the separation between two antinodes is just equal to half a wavelength. So this is half a wavelength, and for this one, that's again half a wavelength. And if you look at the separation between the antinode and the nodes, you'll see that the separation is a quarter wavelength. Okay, this is a quarter, this is a quarter, so that's a half, and then another quarter to complete one cycle. Okay, and the other thing is that frequency, when you have the wave that's been generated, the frequency, wavelength, and velocity, they are related to each other, and the relationship can be described by this: F is equal to V over lambda, and F is the frequency, which is a number of oscillation per second. The unit is hertz, and V is velocity, how fast do the wave travel. So, and the lambda is the wavelength. Okay, so coming back to the first page, we'll find out theoretically how fast the wave travel on the string is can be described by this equation, which is the square root of tension. T here is the tension over mu. Mu is the mass density of the string. Okay, so this is the equation that serves as the base, theoretical value of the velocity. So we need to know that the tension value. We need to know the mass density of the string in order to figure out the theoretical value of the velocity. And then we're going to set up the experiment to find the experimental value of the velocity, and then compare those two values to get the percent error. And so how do we, okay, coming back here, coming down here, so we know that F here is equal to V over lambda. This equation is always true whenever you have a traveling wave. And then applying to the standing waves, which only occur at specific frequencies, then we will label F with the subscript n to indicate which harmonics. So we have F sub n is equal to n over 2L, and then square root of T over mu. So here n over 2L is just equal to 1 over lambda. So we have that here. And then your V, we just use equation 1. So you have the square root of T over mu. So you can see that when you plot F, when you plot F versus n over 2L, then the experimental value of the velocity would just be the slope, which is which when you do a line fit, you're going to do that. So during the experiment, the way for students to figure out what frequencies that they got will be that once you set up change the frequency. So you're going to set up let me see, we have the diagram. So you're going to set up like this. So you have the two rods, and then you have the mechanical driver. So that mechanical driver is going to set up vibration. And there's, on the computer, you can use the software to change the frequency. So you're going to fine tune the frequency in order to find out, what frequencies that the oscillation will be the maximum. And so you can see that, so the length of oscillation of the string is actually considered from this point to this point. Okay, so this is your L here, capital L. And then uh and then uh and then let me change the color. Can I change? And then the tension, we need to know the tension in a string in order to figure out the theoretical value of velocity. So the tension is coming from this. So we're going to put mass on this. So it's going to provide the tension. Okay, and then another string. The string is actually the total length of the string is coming from this point to all the way here. We use a symbol lowercase l to indicate the total length of the string. And you're going to measure the mass of the string. So once you have the length of the string, the mass of the string, then you can figure out the density, because the mass density mu is equal to mass over lowercase l. Okay, so this is how we calculate the mass density. And how do we find out the tension? If you're going to put the loading mass, which we call our loading mass, and we use m sub l to indicate that's a loading mass, then the tension can be found by using ml, which is the mass, and then times g, 9.8, to get the tension. Okay, so once you have the mu, once you have the t, then you can, of course, the theoretical value would just be t over mu. Okay, now when you do this calculation, make sure that everything has to be in SI unit, mass has to be in kilograms, and the length has to be in meters. Okay, all right. And we mentioned that the total L, the total capital L, is different from the lowercase l, because the capital L is where the oscillation, the length of oscillation. So what you're going to see is that you're going to change the frequency, and you're going to see visually to see whether you get the oscillation. So let's say when you choose oscillation, when you choose the frequency, you find that there's a oscillation like this for the first fundamental. You want to continue to fine tune the frequency until you get the maximum, that you only have like just one antinode here. Okay, so experimentally you're going to see you're going to see something like this. Once you set up the right frequencies, then you're going to see, okay, for n equal to 1, for n equal to 1, you're just going to see that one antinode. Okay, and then when n equals to 2, you're going to see, and then when n equals to 3, you're going to see that 3, like this. Okay, so that's basically meaning that the waves, you have found the right frequency for the wave to produce a standing wave. And this, we call that, as I mentioned earlier, this is what we call the first harmonic, and then the second harmonics, and the third harmonics, and so forth. And so they actually, once you find out the first fundamental frequency, F1, F sub 1, you'll find that the higher order harmonics or overtones frequency can be found very easy, can be found quite easily, because your F sub n is equal to the integer, the mole number times F sub 1. So in other words, once you figure out F1, the fundamental frequency, then for the next 9 harmonics, you can just like multiply the integer to kind of estimate where that frequency would be. Okay, when you do the experiments. Okay, so let me see. So let me see what else. Okay, this I just basically a couple of things to bear in mind is that when you set up the setup, on one end this needs to be pushed down a little bit, and this the string has to be right at the center of the pulley, so that it does not produce you know some error to the setup. And let me see what else. Right. Okay. So basically, yeah. So I think that's pretty much what you're going to do for this experiment. Very straightforward. Data analysis, and let's look at the data. So let me look at the data. So the data is this the one? No. sorry. So the data, okay. The data you'll be provided is this. So you can see that this amp here indicate the mass of the string or mass of the cord, which is 12.43 grams. So you need to convert it to kilogram, and the length of the cord is 2.976 meters. And then so you want to calculate mu just by the equation I just mentioned, which is m over l. And then the frequencies, let's say when n equal to 1, when you have the frequency for the first harmonics is 8.3 hertz, and the second harmonic is 16.6 and so forth. So you need to key in those data points to the Excel. So on the Excel, you should have the first column is N, and then the second column is the F, and the third column is that you should have the N over 2 times capital L. Okay. Now, one of the things that so in other words, on the Excel, you should have the N, and you have the F frequency, and then you have the N over 2L. When you do the N over 2L, make sure that when you do the, you are doing this, don't forget the parentheses. You don't just do N over 2 times L. Okay, so when you key in your use Excel to do the calculation, make sure that you put the parentheses so that it is N over 2 capital L. And what is capital L? Capital is 1.5069. And the loading mass is 0.24797. So you can use times 9.8. That will give you the tension. Okay. And so once you have the N, once you have the F value, and you need to calculate this. So so these data points are given. So you need to key into the Excel and use Excel to calculate N over 2L. And then you want to plot F versus N over 2L. And then from the previous equation, we know that the slope is going to give you experimental value of velocity. And then you're going to compare to the theoretical value, which you obtain from equation 1. Okay, and then you do the percent error. So so this experiment, the analysis part is pretty straightforward, very easy to since you've done all the data analysis so far, you should find that this is relatively easy to do. The only thing that student might make a mistake would be when instead of doing n over 2l, they are doing n over 2 and then forgot and then times l. Although they think they're doing the over l, but anyway, that depends on how you key in your depends on how you set up your equation. Again, you should be able to use Excel to do the n over 2l. That will be much easier. I do not want you to key in the calculator to find n over 2l. Okay. All right. So that's basically what you want to do. All right.